The estimate would of course be the median, that's the associated estimate, and there you use all the data, right, so you have 30 data points. And I think that's the middle two. So it's the average of that, which makes it 101.5. The confidence interval, you have to compute the C, right? It's n over 2 minus 1/2 minus 1.96. Now that's for 95% confidence. That's Z alpha over 2, Z.025. If I change the confidence, I'll change this value. Anyways, that comes out to 9.22, and you just round to the nearest integer, so you round to 9. So you want what? C plus 1, you want the 10th order statistics to the 21st. Okay. You do 30 minus 7. So that's 88. Any questions on that? And our estimate of the standard error, we need that tau, but that is just root n times the length of the confidence interval divided by 2 times 1.96. So that whole thing keeps standard error becomes the same. The symmetric confidence interval is not quite the same because the last next I had that error. I changed that. State A is worse than state B. So certain home remedy is supposed to help people with the disease. It was found that for 30 of these patients there were no changes, so we just throw those out, right? The analysis actually gets rid of those observations. And then 14 improved from A to B, right? And then 6 became worse. I asked for a two-sided alternative. And then McNamara's test is the difference, right? Squared divided by sum, 14 plus 6. The off diagonal. So it's 3.20. The critical value is 3.846. Any questions on that? Any questions on the quiz? Sorry for the delay. Okay, any questions on what we've done good last time? The physics? Again, like in the past, I mean, the idea behind the figure of green is we align the samples, and then we fold them, right? And then we check the scale. Again, on that folded thing, the box plot of interest would be the box plot of folded samples, right? Figure of green test statistics, which is a mess to compute by hand. You would never compute by hand. But the computer can, it doesn't have it. Doesn't have error, right? It's so far. So are there any questions on that? Remember, we do turn it into, by taking logs, we turn it into a location problem. then we can get an estimate of the difference, the ratio of the scale error, so we end up with 8.5. So we do get an estimate. Yeah, here again, here's the test statistic where we go to 0. That's what you have to solve for this. See, what I might do today is notes. I'd like to talk about the Variance-Fisher problem. And when you come back, Tuesday, we can start with the paired design. And a lot of the rest of the course is on designs. Okay? We do paired design. We've actually done a two-sample design, in terms of design. Paired design. We'll probably just do the case sample design. Why not? And then the randomized plot design. But then we'll do the regression design. Okay. And, so a lot of the course will be on design. Either you have a design experiment where you have observational data. But from a design experiment, you can often talk about cost. That's what you're rolling out. But often you have just observation data. There's nothing wrong with analyzing that. You just have to be careful with your data. Anyways, we'll talk about that when we come back. We'll start. So today, let's talk a little bit about the Variance-Fisher problem. If we talk about it in very general terms, we don't have a great solution to this, but we do have a solution. You have a sample on X, and it's from some distribution. And then you have a sample on Y. So it's a two-sample problem. And it could just be a different distribution function on the other. And the parameters of interest are the medians. So this would be the population, right? You have two distributions. Something like that. And again, you're looking at those medians. So again, like the shift would be the parameter of interest. Although in this case, we're not going to get a point estimate. Something to think about. Well, you would just use the differences. Yeah, I just would use a bunch. But instead, what we want to test is these hypotheses and do two samples. Now, see if we had G equal to like f of x minus delta, then That would be the location to sample problem, right? And we go back to it. It's just on this thing. So this would be two sample location, right? And you probably use the Mann-Whitney-Wilcoxon in this case. Okay? And then the one we talked about last time, the G was this one, right? Well, this F was this G was this. Then we did a two sample scale point. Now, maybe later on, we can go back and talk about this. We get weights. We've estimated the ratio and scale, and from that you can get weights. And then you can do a weighted two sample location problem, and that's probably what we should do. Maybe later we can talk about it. And then today it's just some G, and we still want to test the median space. Okay. Well, then what procedure can you use? How about the Mann-Whitney-Wilcoxon? And you can if you make one assumption. Now, in the classical Baron-Fisher's problem, this F would be that, that's right. And the G would be this. So this would be the classical problem in the solution here. If you're testing medians or means, it doesn't matter because it's normal. It's the same thing. The solution would be the Welch T. You might have not covered that in your elementary stat class. But it is the default. Actually, if you do T dot test XY and R, it'll come back with Welch's, and it's the default in min-test. So you get to be careful. You're going to have the Welch test. And it's an approximation on the user group. So if you did classical, you'd be looking at phi. Well, phi is symmetric. And for the Mann-Whitney, we dropped the normality assumption, but we retain the symmetry assumption. And I don't see how you live with, because I can show you where we can use it. So we have an assumption. That can be what's symmetric. It's actually the Mann-Whitney version that's more useful in this case. That's going to be our test statistic. And now again, it doesn't change. The stat doesn't change. You could do it with ranks if you wanted to. Combine the data and rank them, and then sum up the ranks of the y's. To get to u, only you have to subtract off this constant that we talked about. So that's not new. So you could work with W too. Okay? So the stat isn't new. The thing is, under F and G, it's you can't use the usual distribution of the Mann-Whitney. Okay, so what can't you use? Well, you can use the mean. The mean will come out to be exactly what it should be. if you assume that symmetry. What you can show under H0 that this indeed is, again, this is an easy problem. I know we've had a lot of notation, but the U form is, if I'm teaching elementary stat, it's often the form I use. What could be simple? You have N1 times N2 matches going on, and you just count the number of times your guy wins. That's what U is, right? So if the Y's and X's are about the same, then half the time X should win and half the time Y should win. So the expected value is very intuitive. It's just N1 times N2 over 2. And that still holds in this problem. So let me show you. Oh, but symmetry, we should talk a little bit about symmetry. Let's say X is symmetric, not 0. Okay. Without loss of generality on 0. Okay. You don't want to use 0, you have to use X minus theta X. You're all tangled up with that. So then your distribution does look like this. Okay. Well, I mean, it doesn't have to be line-shaped. It could be this for the people, or it could be uniform. So there'll be there's a point of symmetry. This is not block. This is better. Well, the thing to do is take points X equidistant. What's the probability of X? We could draw a little rectangle here. What's the probability of minus X? Well, if this was a symmetrical drawing, these would be exactly the same. Right? It doesn't matter. This one too. Took an art class with my wife years ago. She does art using pastels. So I did pastel class with her. Of course, I flunked. But then these would be equally likely. But that says that the distribution of X is the same as the distribution of minus X. Right? Okay, you observe X, but guess what? In my country, we always observe minus X. So you observe little x, and I observe minus little x. But if it's symmetrical, then the probability of those things occurring are the same. So we say law notation. Okay, so going back to the Woodley, distribution, this says the distribution of minus x is the same as the distribution of x. It does not say that minus x is equal to x. It's a big difference. But if you're working on a probability problem, and you'd like to use minus x instead of x, and you have a probability statement, feel free to substitute it in. And I want to do the same thing with Mann-Whitney, so we're going to assume that f and g are symmetric. And then, without loss of generality for this argument, the medians are 0. Okay. Actually, I want symmetry. This is without loss of generality. That's what that stands for. Without loss of generality. Now I'm looking at the Mann-Whitney, so I'm looking at these things. Yeah, those are the differences in the unwritten. But then I'm just writing word, okay, that's word base. This is all out. That's the same statement, right? But then minus y has the same distribution as y, and minus x has the same distribution as x. So I'm making a distribution statement of y. So I'll just put y. So that's it. See, I get that statement. This is the law of this. And that's really all that's the thing I needed. And this I'm not going to write down. That's really the gist. I need that, okay? I need to show, whoops. I need that result. Let me show you this. And then you can I'm after the expected value of u, and there might be an easier way of getting it, but this will work, right? U can be written as what? It's the number. Let me just explain this little piece of notation. It's a number of use this, right? Well, there's a hard way of doing this, and that is you just look at each pair, and if this is true, you add 1. If it's not true, you add 0. Well, then if you add all those things up, you will get u, right? And that's all this says. This will be 1 if yj is greater than that side, and it's 0 if it's not. So if I add all those up, I'll get u. So I'm after the expected value. So the expected value is linear, so it's the expected value of these things. Right? But all these things have the same distribution, so it's just n1 times n2 times n. They're all the same. They must have the same. But there's the distribution of y minus x is the same as the distribution of x minus y. So I can just write it that way. And then it's either 1 or 0, so you can look at the complement and subtract it from 1. That's what it says. There. Well, then you end up with n1 times n2. The expected value of 1 minus this is 1 minus the expected value. So you have n1 times n2 times 1 minus. didn't want to take this on. So the expected value of u is equal to n1 times n2 minus the expected value of u. So the expected value is so it has the same mean as in the Mann-Whitney Wilcoxon two-sample. Alas, the variance is not true. The variance is not right. And, so what we do is we estimate the variance.
Where did the divided by 2 come from?
Well, now I just take this on the other side.
Oh, okay.
And we can estimate the variance, and we don't have time to go through it. And, it's, we have these simple tools, and it's a problem. When the problem gets complicated, the method gets a bit complicated. Okay. And again, in the old days, then you couldn't do it really. In the new days, we can. The computer's going to do all this work. You end up estimating the variances of these things called placement, and they're described in the notes, okay, that you have. So I don't think I'm going to go over it. I don't ever see you doing this on a museum, figuring out the placements. So you can standardize the statistics that way. But the computer can do it. And, and then finally, here's your z-statistic. So you take the old Mann-Whitney Wilcoxon, okay, or Mann-Whitney, but you could use W, you just have to subtract off the right mean. But this would be the mean of u, right, under the null hypotheses. And then you standardize it by what these things are called placements. Yeah. And then you reject it to see if this would be a two-sided test. Any question on that? This is called the Fligner. It's the same Fligner. It's called cello. And you write it as many violins. That's George Paulicello. He was a graduate student. He was 1 year ahead of me. Penn State, thousands of years ago. He did some nice work, and then he decided to make money in industry. So I worked with George for many years. Okay. So of course, it allows me to get to the web today. I think I called it FP stat. It's an R program, and if you put X and Y in, it does, I would go Y minus Y X, because Y over X. And then you could change the alternative in things. I don't have an estimator connected with this at the moment. I guess I would just do them. There it is right here. But you can just download the source. You can change delta and you can change that. But if you don't do that, it's just after the transform. But it is X over Y, that's what it is. I think I should check that. Okay. So when you come back, we could do, we should spend a few minutes at the beginning of the class with Tuesday going over this. We could do, do the figure, we do a couple of problems, we could do the figure scale test and this figure and Paul very Fisher. It's easy to do, you just have to source those programs in. Okay? And you don't have to look at the code. Any questions on that? Okay, so we're actually, since we're done with the two sample problems, except we can repair designs. Back. And so we'll take off the Maryland designs. So, but then we'll have to use the computer a lot more as we go along. There's no free lunch. Most of you use the computer now. 10 years ago, I used to have lecture the students that they have to use the computer. This is a computational world, so you've got to learn to use it. Okay, so start out, and I'll pass out the quiz. Again, turn off your laptops.